Hello, everyone. Welcome back to SAT Math Question of the Day. Today is Friday. We missed Thursday. Oh, I'm so sorry, but we did. So because we missed Thursday, we're going to do Throwback Thursday today on Friday. Throwback Thursday is when we take a question from the test before 2016 and show you what was on test before then. Anyway, here is today's question of the day. It is a calculated question, and it's got a lot of words, and my suggestion here immediately, we're here to hopefully show you how to approach SAT math questions. I can tell immediately, read this question really carefully, really carefully. Okay, here we go. The tables below give the distribution of high temperatures in degrees for city A and B for the same 21 days in March. Okay, fine. So there are a few days that are 80 degrees, and most of the days were wow, must have been a warm city.
Okay, what's the head of the first column?
City A.
What is the head?
Oh, temperature.
There are two tables.
Yeah.
Two columns each.
Right.
The top table is for city A, bottom for city B.
Right.
What is the leftmost column for in each table?
The temperature.
What is the rightmost column?
How many times that temperature occurred in 21 days in March?
Okay, what is that called?
Called the frequency.
Good.
Okay.
So you read. So we're reading the tables.
We're reading the table. Now we are going to read the question. Which of the following? Okay, what's true about this stuff? Okay, what's true about the tables? Now we got to read this really carefully. The standard deviation of temperatures in city A is larger. The standard deviation of temperatures in city B is larger. The standard deviation of basically the same. The standard deviation in these cities cannot be calculated with the data provided, so I don't think that's true, right? So now we have to know what standard deviation is. Standard deviation, when you have a bunch of data, is how wide is the spread above and below the middle number. So if this would be a very low standard deviation, because see this distance, see the red distance is smaller than the blue distance.
Okay.
The blue distance.
Okay,
right?
Joel, notice I drew those curves.
Good.
But I drew them vertically.
Yeah.
Right?
Yeah. That was very efficient.
As they usually people show these curves horizontally.
Yeah.
Right. But in the form of the question, the way to easily observe what those curves look like is to draw them vertically, which I did in red. Right. And so obviously, this is the one, the standard deviation for the distribution on city A is larger. It's more. It has a prominent bump and a lot of lows around it. The other one goes up, it goes down, up, down. Doesn't go very high where it goes high. So in terms of this, yeah, I think it's better. Joel, if you're going to plot the standard deviation, I think this is a large standard deviation.
Right, yeah.
Okay, let me draw one on the same axes with a small standard deviation. Instead of drawing it, you can't really tell because your scale is different.
But come on.
For a small standard deviation, it would.
Common sense.
For a small standard deviation, let me draw. It would look like this.
Okay.
Like that.
Okay, fine.
On the same axes.
That's fine. So what's the answer here?
The difference is, you can't really compare this blue thing here with the blue thing here because the scales are so different.
Okay, fine, but let it go. We know what we're talking about. If you have a graph...
No, our audiences don't know what we're talking about. We have to teach them.
Yes, they do. If you have a small spread, it's a small standard deviation. If the graph looks like this, it's a small deviation. If the data is all spread out, it's a large standard deviation.
Actually, no. If you take the same graph,
yeah,
you take a graph and magnify it in both directions.
We're not doing that.
If you did if you take the same graph and magnify it in both directions, the two graphs will have exactly the same standard deviation.
Stop all this. Let's just get to the answer.
Okay, but the point is, do you see my point?
No, I don't see your point.
It is misleading to draw a little graph here and a big graph here.
Stop, just get to the answer. Just forget, let it go. Let it go. Just get to the answer. What do you think the answer is? A or B?
Oh, gosh. It's A is larger standard deviation. No, it's actually B has larger standard deviation.
Right. You were heading the wrong way, by the way. You were talking so much you didn't even want. You were heading toward A. No, B
that's right. Oh wow.
Deviation because it's smoother. All you have to see is that it's more smooth. It's like all over the place. It's like smooth. It's like if you graph this thing, you get a flat thing. More like this. More like the green thing. Flatter. So I would say it would be B. Because A seems to have a peak. Now, actually, if people are really good with calculators, they can actually calculate the standard deviation for each of these with their little calculator, the TI-84, and actually get the actual number. And if you're good with calculators, you're fine to do that. So I would say it's B. That's what I would say. Now I will look up the answer. The answer is math calculator question 23 is B. We got it. We got it. Yeah. So standard deviation is basically how spread out the data is. If it's spread out all over the place, it's a larger standard deviation. Okay. Now notice that you're not ever going to have to calculate a standard deviation on the SAT, but you have to know what the standard deviation means. That's the critical thing in problems like these.
Okay. So again, I think what made it really clear is to plot the frequency going up and down along the sides of table A and table B.
I must admit that was really a good idea.
Yeah.
That was a really good idea, which certainly did not occur to me, and probably doesn't occur to most people.
That really automatically, notice that the scales are identical.
Right.
There's 80, 80, 79, 79, 78, 78. They're identical scales, and the height of each table, H. The height of each table is identical.
Right.
And then if you make like 14, this is about 3. This is about 14. This is about 3. This is about 6. I did it to scale. This is also 6.
Yeah.
So these are plotted the same scale in the same vertical.
Right.
Same vertical, same horizontal.
Right.
Here, these scales are different.
Yeah, but that was
okay.
Qualitative.
That's my criticism.
Fine. I did it qualitatively. Okay. Fine. I did it qualitatively. But the whole purpose of this was to discuss what a standard deviation is. It wasn't meant to be to scale. It wasn't meant to be to scale. It was meant to be qualitative. I know. I get disgusted by it. By the way, Seth, when you said the same scale, this could have been a 30. This could have been a 29. This could have been a 28. This could have been a 27. This could have been a 26. And it still would have. As long as they're separate by 1, it's the same answer. Yeah. Because they're interested in the standard deviation, not the actual numbers.
Yeah,
right?
Well.
So, right? I mean, if this was a 30, 29, 28, 27, 26, it wouldn't change anything. Because
right,
yeah. That would have been a cold city. City A would be a cold city, and City B would be a warm city. But City A is a cold city with where the day tended to be like the same temperature on the same day, same temperature on a lot of days, same temperature on a lot of days. So we're done. We're done.
Yeah, done with
Ready
that.
For Throwback Thursday. Let's go
Throwback
back
Thursday.
Time. today's Friday, but okay, Throwback Thursday. Sometimes, yeah, that happens. Now we have this feature, this program called Zeitboard, which is very nice. We have everything posted, and it just takes a second. So what is Throwback Thursday? But after 2016, the SAT people over in Princeton decided to change the nature of the test from more of a IQ type reasoning, boy, you got to be like really clever, to really just stuff you do in school. And so these questions predate that, when you had to. A lot of the questions felt very different. I forgot if this is a calculator section or not. Well, forget it. There's no calculator here, right? I mean, it doesn't matter whether it's a calculator section. You're not going to use a calculator in this question. Okay, so as you can see, it has a whole different feel to it. So we're going to both be quiet. I guess you should try it. Stop the video, and we'll see how to do this thing. Okay, here we go. Change to black. Single line, like Seth like. Okay, here we go. Step 1. Choose a number greater than 2. Aha.
Okay.
If the prime at 5, it's not at 5, right? Divide the result of step 2 by 2. Okay, got it. Yeah. Find the greatest integer less than or equal to the result of step 3. Okay, fine. Okay, that's the rule. Now, in the chart above, if the number n is chosen, in step 1 is 39. Oh, so is it just to follow the flow chart blindly and brainlessly?
Yeah.
Yeah, so this just tests your ability to follow directions.
Yeah.
No, so there's really not much. You just have to follow directions, right? So how about if we take turns? I'll do step 1, you do step 2, I'll do step 3, and you do step 4. Is that fair?
Yeah.
Okay, I'll do step 1. If the number's just 39. Oh, well, okay, 39. Okay, Seth, you do step 2.
Okay, so I'm going to do it at the bottom.
Go ahead.
39. If it's prime, add 5. Well, it's not prime because it's divisible by 3.
Okay.
If it's not prime, add 2. So I add 2 and get 41.
Okay, for now I do step 3. Divide the result by 2. So that would be 20 and a half. Well, maybe a calculator would be helpful, but maybe calculating would be helpful. Okay, 20 and a half. But I don't know if we calculate a section. I don't know. Okay, go ahead, Seth. You do. Finish it off.
Find the greatest integer less than or equal to the result in step 3. Well, 20, right? You can't think of it. This number is between 20 and 21.
Less than.
20 and 21 are the integers near this number, and the greatest one that's less than this number or equal to this number is 20.
Yeah, so it looks like the answer is 20. Okay, yeah. I don't know if we have the answers to this question, this test, so we'll just leave it at that. Wow, so this question looked like, just visually looked hard, but actually it was just following the rules, right?
Yeah.
It doesn't seem like this question would be on a modern test, would it? We never really... there's really nothing to this.
Yeah.
Yeah, I don't know.
Yeah. Okay.
Like
well, yeah. This is what you would learn. This is what you would learn when you start at the very beginning at learning about programming computers.
Right.
This is the form in which computer programs are.
Yeah.
It's called when it's written this way, where the steps are described precisely, but they're not in the form of a programming language. It is called an algorithm. So this is an algorithm with 4 steps, and the question is, when the input to the algorithm is 39, what is the output?
Right. Okay. I mean, there's really nothing to this other than following the rules. But there's a tree. There's a tree here that may confuse some people. Okay.
Well, it's an if. So those if.
Yeah.
additional things.
It's an if statement, you know, an if thing.
Notice that when you get to step 2, in this example, 39, you find that n being 39 is not prime, and so you could merely skip this part.
Right.
Don't bother adding 5.
Right.
Okay?
Yeah. Okay. I think we're done. I don't know there's
Yeah,
much else to say here. Okay. Boy, that was pretty unsatisfying. Oh my God.
Should we do another one?
Oh my God. Oh, this is not going to go down well for me. How many positive integers less than 1,000 are multiples of 5 and are equal to 3 times an Okay, you would never see this on a 2016 test, would you? Opposed to that. I don't think so. This is like number theory type stuff or analysis. How many positive integers?
Number theory, yeah.
Obviously, you're not going to be counting these on your fingers. Positive integers less than 1,000 are multiples of 5 and are equal to 3 times.
Okay. Now, a number that is 3 times an even number is a multiple of 6.
Okay.
So it's looking for numbers that are both multiples of 5 and multiples of 6.
Oh, 3 times an even integer is multiples of 6. Yeah, right. Yeah, even the lowest even integer is 2. So, yeah. Okay.
Yeah.
Wow. Multiples, so a numbers less than 1,000, can't be 1,000.
Yeah.
And
it's greater than 0.
Right.
So what are those numbers?
And then multiples
of 5 and multiples of 6.
Like 25.
Well,
5. 30. 30 is 1, right? 60 is 1. 90 is 1, etc. But there's more, right? 30, 40, 45, 50, 55, 60. Oh, yes. It looks like they jump like that, right? I think they go like this, right? Oh, it's not. Maybe you can figure this out, right?
No, are they 5? Let's see. 5 times 3 times 2 is 60. They're multiples of 60, right?
No, 30. 30 also, aren't they?
No, 5 times 3 times 2 is 5 times 6.
30.
Which is 30.
30.
So the multiples of 30.
Oh, I see. So you had to be really clever though to figure this out. That's a cute way of saying multiples of 6. Probably on the modern SAT, they may have said multiples of 6. 5 and 6, rather than 3 times an even number.
5, multiples of 5, and multiples of 6.
Right, yeah. But this is tricky, right? This is a 2-step problem. Yes. You got it.
So the multiples of 5
wow, you can almost...
that are greater than 0 are 5, 10, 15, 20, 25, 30, 35.
No, we're done. 40, we know the answer. It's this.
45. And then the multiples of 6.
Yeah, but this is the answer.
Are 10. Oh, sorry, 12.
Seth, we know. We're done. We know they're multiples of 30. Yeah. You don't have to do that anymore.
Okay.
We're done. We don't have to do the analysis. It's multiples of 30.
Okay.
So, I mean, just should do it by brute force. You start with 5 and you know it's 6, so you can just go like this. So how many of these numbers do you have?
So you divide 1,000 by 30 and round down.
Right.
So that's 33 to third, so it should be the answer is 33. Right?
The answer is 33? There are 33 numbers between 30 and what's the highest number?
1,000.
No. But 1,000 is not divisible by both 5 and 6.
No.
1,000 is divisible by 1,000 divided by 30 is 100 divided by 3.
1,000 divided by 30.
It's 33.
Equals 100 divided by 3.
So it's 900. 990 is the highest number. Right?
Yeah.
So how many numbers are there between 30 and 990? Oh, God. It's getting really messy. Seth wrote, but
I think it's 33.
990. 33 numbers? Between 30 and 990? Not 31.
Including
not
the 30 and including the 990.
Yeah. Not 31 or 32.
No.
Okay.
Well, let's see. Let's see if we do it another way. The first of the numbers that are multiples of 30 is 30. So that is 1 times 30. 1, oh, come on, times, come on, 1, oh, what's wrong? Times 30 equals 30. 2 times 30 equals 60.
Right.
So forth. So the answer times 30 equals 990. So 30, what number times 30 equals 990?
33.
Well, that's 33.
Good. So that's another way to view it. Yeah. You know how yeah.
So we count up 1, 2, blah, 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 up to 33.
Right. So that's one really good approach. Let me offer another approach that I use, which is sort of stupid, but maybe other people use it too, but I doubt it. Okay, let me show you this approach. Right? I have no idea. We know the answer is around 33, but I have no confidence as to whether it's 31, 32, or 33 because counting is tricky. Like, how many numbers are there between 0 and 5?
Depends on whether it's strictly between 0 and 5 or inclusively between 0 and 5.
I meant no. How many numbers are there between 8 and 12 inclusive?
Inclusive.
Yeah, 8 and 12 inclusive. How many numbers are there between 8 and 12 inclusive?
Well, let's see. It's
most people
5.
Most people would say 4. Most people, if you're not thinking, most people would say 4 because 8 and 12 is 4, right?
You know what? I do it on my fingers.
So do I. That's why we're brothers.
So 8, 9, 10, 11, 12 makes 5 fingers.
That's how I do it. Wow, that means I must have learned from you. Of course, if you were asked a question, how many numbers are there between 8 and 12? Fingers, 8, 9, 10, 11, 12. Okay. Do not do it up here. So that's why I'm a little concerned here, right? I mean, is this...
Okay, well, I have been trained after doing it with fingers many times. I actually know the rule.
Okay, but we're not talking about that right now.
You could also solve that problem by applying the rule.
Seth, nobody knows the rule.
I know the rule. You take the difference and add 1.
PhD in math, and you've been doing math for 62 years or something. So forget the rule. Yeah. Forget the rule.
But why not tell people what the rule is?
You can tell the rule after I'm done. After I go over the stupid way of doing it. Okay, you do it the smart way. I want to do it the stupid way. Okay. After I do it the stupid way, you can then tell the rule. Ready? Okay. So I have no idea whether it's 31, 32, or 33 because it's so tricky, right? No, 30, 32, 33, or 34. Okay, I really don't know. I know it's one of these
32, 33, or 34.
Right. Okay, so this is how I do it. Now, again, this is a really dumb way of doing it, right? I make a simple example that I could do with brute force. I change the problem. I say, how many numbers are there that are multiples of 30 up to 220? Up to 220, right? So I say up to 220. I divide 220 by 3. I get 210. I realize the 210 is the lowest number below 220. And then I write, look, I already did it. I literally count the numbers that are multiples of 30 up to 220. I'm going to count them. 1, 2, 3, 4, 5, 6, 7. Wow, look at that. 7 is equal to 210 divided by 30.
Okay.
That's a nice example.
I have an even dumber way to do it.
Seth, I'm not done talking. I'm not done. So then what I do is I apply my little thing, which is not a mathematical proof, but, it makes sense. And then I apply it to my 990. 99 divided by
Okay,
30
Joel,
is 33.
apply it. How many multiples of 30 are there between a positive, how many positive multiples of 30, non-zero, are between 1 and 40?
Can't think like that. I have to have an example that's
All right,
that's like
all right.
this.
How about between 1 and 70?
Well, that would be, you go down to 60 and you divide by 3. You divide 70 by 3 and you get like 20 is, no, 70. You go down to 60. 60 divided by 3 is,
By
60
30.
divided by 30. 60 divided by 30 is 2. So there the answer will be 2. And 2 is 60 divided
All
by
right,
30.
why can't you do that with 40? To
Because
go
I
down to
already-
30,
Seth,
and you just have one of them.
Seth, don't you see? I already wrote this down on the paper. I already wrote
All right.
this down on the paper. So then it's,
Yeah.
then
Well, no, the same method of remembering the rule works when the answer is 1.
Look, I don't know the rule. Most people don't
The
know
rule,
the
the
rule.
the rule is that you is that you subtract the okay, let's see,
What rule are
they're
we talking
inclusive. They're inclusive endpoints. So the rule is you subtract them, add 1, and divide by the number you're fitting in,
Forget the
and then round down.
No one's going to know the rule, okay? No one's going to know. The only people are going to know the rule. People with a PhD in math, and
Yeah.
those people are not taking the SAT. So forget the rule for most people. Okay? Just forget the rule.
Yeah.
Just you got to just use. There are at least a few. There are a few ways to do this.
Yeah, yeah.
Okay, and yeah, so really smart people will do the way Seth and will know immediately that the answer is 33. People who have to be a little bit more cautious would be, would have to think a little bit more about it. But you got to be really careful when you're counting, because how many numbers are there between 8 and 12 inclusive? 5, not 4. Be careful with counting.
Yeah.
So
Okay.
So this is one of Seth's expertise, because Seth has.
Well, this is also comes from. It also comes. It's something that you have to deal with. Often you have to deal with in computer programming when you're indexing arrays.
Yeah. Well, people
working
are not,
through arrays.
People are doing that. Yeah.
Yeah.
Okay. So this was a bit of this does not feel like a post 2016 question, but this
a pattern
is really nasty.
a pattern that occurs frequently in programming languages is you specify a range of numbers by giving the first number that's in the range and the first number that is larger than the last number in the range.
Okay, Seth, we're going off topic. Okay. Why don't we get back to topic, to the thing that's the really hard part about this problem, which is how do you know this is a synonym for multiple of 6? That seems to be the hitch in this problem also. That's a toughie, right?
Okay, so what is a synonym for an even number?
A number that's divisible by 2.
Yes. Okay, give me another synonym for an even number.
Another synonym for an even number?
Yeah.
I don't know. Not number divisible by 2? I don't know.
It's a number that is formed by it's an integer that is formed by adding 2 equal integers.
Okay.
And in algebra and in arithmetic, we have the fact that if you have two numbers n, you have 2 copies of the same number n, n plus n equals what?
2n.
2n. So a number, that's called E.
Okay.
An even number is both a number that's obtained by adding the same integer to itself, and it's a number obtained by multiplying an integer by 2.
But what does it have to do with 3 times the number?
So here, kids are taught even numbers.
Right.
The first time a kid is taught even numbers, she is taught in terms of sharing. 1 for you and 1 for me. 1 for you, 1 for me.
Okay.
Right?
Yeah.
The same number. So an even number means a number of things that can be, the words are used, divided evenly.
Okay.
Okay? So that means the number obtained by combining 2 equal numbers by adding them.
Right. Okay.
And then a few years later, they teach multiplication.
Right.
And adding the same number to itself means you add it with itself together 2 times is
right.
multiplying by 2. Now, in this question, they combine the concept of being 3 times a number with the concept of being even.
Okay.
Now, being even, it's hard to. It's two different kinds of concept. 3 times, not multiple times, and a number obtained by adding to itself. However, the SAT is based on what? 10th grade math, 11th grade math?
Something like that, yeah.
Not 2nd grade math.
Right.
And so they expect you to know that a number obtained by adding the same number to itself is obtained by adding the same number to itself, n plus n, and that is the same as 2 times n, which is obtained by multiplying the number by 2. So they expect you to combine one characterization, multiple by 3, with the other characterization, multiple by 2, and it's of, so it's a multiple of 3 of a multiple of 2.
Okay, fine. So I'm starting to see what Seth's talking about, but let me try to explain it like maybe. So the way I would say it then, thanks Seth for explaining, I finally understand, is that an even number can be written as 2 times n, and n doesn't have to be even. An even number is 2 times n, where n is an integer. And they're saying 3 times this 2 times n. So what they're basically saying is multiples of 6, right? Because they're saying every even number can be written 2n. Then you multiply that by 3, you get 3 to 6n, and that means multiples of 6, right? Then you take the big 3, and then you see multiples of 6. Okay, got it.
Yeah, so they call it they call it the associative law of multiplication.
3 is equal to 6n, and that's the key to the problem. That's the secret.
Yeah,
that's the secret.
That 3 when you first multiply by 2 to get an even number, then multiply by 3, is the same as just calculating 3 times 2 to get 6.
Right.
And then multiplying the 6 by n.
Right. Okay, fine. So I think hopefully we explained how to do that. But you'd have to do that without help on the SAT. You have to figure that out yourself. Okay, so that's a little bit tricky. Okay, everyone. So have a great day. Today was Throwback Thursday, but it's really Friday. Have a great weekend, and we expect to be back Monday with another SAT math question and show you how to approach SAT math questions. Please put comments on our videos and email us SAT math questions at satmathquestionoftheday@gmail.com. And everybody have a great day.